Hello. So lately I have been experimenting with Docker, Kubernetes, and k3s. And I thought I started to make some videos to share basically what I learned. So what is Docker? Basically, let's begin with that. A Docker container is a packaged application, and it includes all the necessary dependencies and configurations to move it, share it, and run it. So there are some benefits of why to using that. Basically, most people that hosted stuff probably know, but the de facto before containers was virtual machines. There were some other technologies in the past like jailkit or chroots or OpenVZ and LXC, but they never really got widely adapted and were mostly a thing covered by the operations part or operation teams. So basically, Docker, compared to virtual machines, does not have their own kernel running inside the virtual machine or inside the container, but uses the kernel from the host system. So if you have a lot of containers running, you will notice a big impact. So in case of memory, it will use less because you basically don't have to run a container, a kernel for each virtual machine. The biggest benefit why I think Docker got so famous is because it's developer friendly. So it starts with having a Docker client, which is basically what you use when you run your command line stuff. That then calls to the Docker daemon. It also has images. It's basically how you package your applications. And then you can ship these into repositories, and other people can grab these images and add stuff on top of these. And you also have the Docker Compose, which is like another command line tool on top of Docker, which allows you to run multiple Docker instances and create separate networks easily and stuff like that. That has been very easy to a non-operations guy to get stuff up and running and then hand it over, which Inform then sort of created a standard between developers and the operation teams. And that is also like the emergence of the DevOps, where you have teams working together, developers and operation people, and shipping applications together. And Docker is a good standard between these teams. You then have, I mentioned these earlier, the public image repositories, and that is, I think, one of the biggest impacts why it grew so quickly. So a lot of people could just easily grab some web server with all the stuff that they needed to run their certain application and just focus on developing. And it also makes it easy to switch back and forth between versions, because you basically create images and you tag image versions, and then you can jump between the versions quite easily. There are also some downsides to using Docker. If it's easy to get working, you can easily expose too much stuff or use some default images that are supposed to be used for testing stuff, and everything is widely exposed. A big concern coming from the older stuff like OpenVZ and LXC and stuff like that, you always had the issues of resource starvation, where basically all the containers share the same kernel and the same resources. And if one of these goes wild and has some bug, or somebody's using it in a way that it shouldn't be used, so it ends up taking up all the resources and starts the host, and then all the other containers sort of crash. On a virtual machine, you have that stuff sort of more isolated. And a virtual machine is also sort of another layer of abstraction, and it comes with its own kernel. So basically, a virtual machine is, when it comes to security, it's a little bit better. But due to the fact that it's harder to maintain it, you might have it easier with containers to keeping up security, because you can more easily patch stuff and update stuff. So it's always mostly a use case. There are some things when it comes to security that you should look into, but this is a little bit too much for this small video. So the next thing I ask myself is, how do they work? And then I looked up, and Docker is basically written in Go, and it uses mostly the kernel namespace features, which are part of the Linux kernel, I think version 2.4 or 2.6 or something is when that started. And there are basically a few. I wrote up the most important ones. So one of these is the PID namespace for separating processes, the net namespace for separating networks, IPC for inter-process communication, the MNT for mounting volumes and shares and stuff like that, and then the UTS namespace. So they are sharing the same Unix time sharing system. There are further things used like cgrips, but the core of Docker and that container technology is using the Conda namespaces. And I wanted to take a look at how these look like. So if we take a look at my process tree, let's do it down here and maximize. So I am basically running on an Arch right now, and I have systemd. And inside systemd, I have dockerd running. I also do have containerd running, and we'll get into what these are in a bit. The next part is that I created a Docker file to basically create a test image that I can compare how the host and the container see the processes. For that, I used the last Debian version, created a group called Docker group, and then added a user called Docker user and added the user to the group. Then I installed the proc CPS tools, which allow me to run the PS tree inside the container. And then I am basically just running a command so the container keeps on running. So once that is done, we can start building the container. For that, we run docker build, and then we specify a tag, and we call it Debian on root. Oh, yeah. There is an L missing. So that in turn will follow our Dockerfile instructions and create the group, install the package, and build everything. It went quite quickly because I already built it here to speed it up. And once that is done, we can then start turning the image into a container by specifying how we are going to run it. In here, we are going to specify the -v that stands for volume. So I am basically mounting the current directory to the home Docker user shared folder. And then I also specify the -it for interactive terminal, and then the name that I specified when building the image. And lastly, the executable inside the container we are going to run. And that will create a session and log us right into the container. And then I can go to the home folder of the Docker user and run a lsla on the shared folder. And you can see I mapped the shared folder inside the shared folder on there, but that doesn't really matter. What's important to us is if we look on the host system, inside the shared folder, you can see that the files are owned by the user locale and also owned by the same group. But inside the container, it is owned by the Docker user and Docker group. And that is roughly how you can think that namespaces work. They are like some table. And in the table, you have the process IDs, the user IDs, and all these things per container. And you have a value for the host system and a value for the client. So if we look at processes, let's run the watch -n1 to run a command every 1 second. And what we want to do is to display the process list. You can now see that it's starting 2 watch commands. That is how this tool works. So basically it has one main process and that then spawns a child process. And it's basically creates that every 1 second. And that child process then runs the actual command. If we are now going to take a look at the host and grep for the watch command, you can see that the watch command here has a process ID of 36420 and is owned by the user lookin. inside the container, we have the watch command running, and we have a process ID of 7. And it's actually executed by the Docker user, the one user that I'm basically starting the process with. So you can see it's like containers work by mapping stuff into namespaces, and under the hood, Docker then creates separate namespaces for all your containers and make sure that one container cannot touch stuff it's not supposed to touch. So if we now take a look at process tree again, you can see that the Docker stuff is still running. That is the daemon, and that's managing all the stuff. And then we have containerd, which is the runtime environment or requirements. So basically, containerd is some sort of abstraction that makes it easier for developers that work on higher level stuff to interact with the kernel namespace stuff. And then containerd runs runc, and runc then in turn is basically a small CLI2 which spawns and runs the actual containers according to OCI specifications, I think. So yeah, that is roughly how it works. I will link a video in here from Live Overflow, and he goes much more into depth on this topic, so definitely check that out. What's maybe also interesting to know is the difference between images and containers, to make sure that everybody understands that. So image is what we build when we define our Docker file and then run the build command. And that is sort of like the application, like all the dependencies that it needs to run. But we also have the configuration. So when we run the Docker run command, that will turn the image into a container by adding informations like the volumes or the name and stuff like that. So how do we interact with images? We can, for example, just do a Docker image ls, and that will list us the images that we have, and we can pull images. And you can go to hub.docker.com, and that is basically the biggest public repository of images. And you can search for what you need and grab these. So now we basically downloaded the Docker image for Redis. And now let's turn that image into a container by running it. And this time we are going to specify the -d. That means detach. So basically run it and spawn it into the background. Then we give it a name. Let's call it Redis test. And then lastly, we specify the image name. So that now basically gives us a long ID. And if we run docker ps and take a look at what's running, we now have Redis running. And you will notice that the first, I think, 12 digits of that container ID is the same as that. So you can interact with Docker by either using the name or by using the ID. And you can use the short ID or the long ID. So if we now look at our containers, we can, for example, just stop the container by using the ID. And we can then take another look what's running. And we can also start it. Back up by using the ID. And we can also stop it by using the array, the name, which is Redis test. And of course, we can start it back up by using Redis test. So now I actually want to stop it because I need to change the configuration. So let's first delete it and now run it again. And this time I am going to map a port, so 12345 on the host, to 6379, which is the default Redis port. Redis is a key value database, so you basically send it a name and it gives you a value back. And that is really good for testing stuff. So that will be executed inside the container, and we want to be able to access Redis directly from the host system. So I have to map that port. That's why I'm adding the -p flag. Now we are also running it in detached. We are giving it the name Redis test again. Oh, let's just call it Redis test 2 and then specify the image. So now we basically ran that, and if we check port 1, 2, 3, 4, 5, we can now see that something is listening on this port and waiting for connections. And we can connect to it directly and issue any sort of commands. Info is to show the general stats. Okay, so we have basically Redis up and running. What might be also interesting is if you want to debug some stuff, you can usually just type docker logs and then the name of the container, and it will show you all the logs. By default, you package one application in a container, and it basically prints the input for the standard output and the standard error stuff onto the logs. And of course, you can also run the IT stuff again to get an interactive terminal inside the container and then start debugging or changing default values like that for testing, and then making changes permanently by modifying your Docker file. But yeah, I guess that is just a simple instruction on how Docker works. And in the next few videos, we will do some more hands-on demoing. So speak to you soon.